So yes, as I was saying before the break, it's nice to play with the parametric approach to design that we have in Grasshopper, and with the um, elements definition regarding Revit elements, Revit architectural or structural elements. So, for example, I wanted to show you how easy can it be to create some particular architecture, something that is also easily recognizable. So, for example, let's turn off all of these things. Here we have the example for the interconnections. But anyway, let's focus on very simple things. I will run quickly through a uh, definition of a tower, for example. So it's we can use several methods, of course, to define this kind of geometry in Grasshopper, but I would just try to use a simple approach. So, for example, something like this, and this defines the number of stories that we want to use in our tower. And then we can, for example, change the aspect of these levels. So I'm going to take the geometry, the center of each floor level, and use the center as the center of scale. And I'm going to define a variable scale factor using, for example, a graph mapper. Probably this is something that you are already used to, but nevertheless something that it's pretty nice to see. So we have 50 elements, 50 floor basically. We need 50 scale factor. So if I plug this here, I get 51 values. So I need x minus 1 to be the amount of values. You see that now they're 50. And I want to use as the law for defining the scale factor. I'm going to use something like a Bezier curve. And I want this tower to start with some particular, let's say, diameter at the base, and then increase it, and then make it fall down like this. And so if we turn off the original array, we see what shape we are giving to this tower. Now, the problem with the array of these circles is that they all share the same orientation. So if I bake this it's always a mix between geometry, topological analysis, and architectural element definition. If you take this curve and activate the control points, you see that they all share the same orientation. So most likely their seam point, meaning the starting point of the circle, is aligned along this quadrant here. And now as I want to define a particular alignment or orientation for the columns, for the elements of this thing, of this building, what I need to do is also a rotation of this object. I can use word XY plane because rotation is a planar operation, while scale is a three-dimensional operation. So if I say that all this geometry rotate around the XY plane, each geometry will rotate at its own height. It's not going to fall down. So this can be left like this. I only need to define the angle. We can work in degrees. And once again, I need to define a one rotation angle per each cross section, per each level. And I only need a linear progression for this rotation. And so I will get here 50 values for the rotation. I will convert these into degrees, like remapping them from their original range, which is between 0 and 1, into a target range which is between 0 degrees and I don't know, something like 180 degrees. So yes, basically this gives us the mapped angles in degrees. Okay. So in this moment, well, basically there is no rotation. If we evaluate, for example, these curves, or if we directly divide these curves with a series of points, from the top view, you will see that all points are aligned like this. But if we start increasing this rotation, you see that we start getting spirals along the surface of this thing. And therefore, we can use, for example, this rule for defining the beams, sorry, the columns or frames in the facade, depending on how you want to, let's say, define the structure of this object. Okay, so if you have these, you can flip matrix these objects. So the points are now sorted by in, by vertical orientation and not by horizontal frame, horizontal curve. And so if we connect them with polylines, we will get this vertical connection system. They are polyline. They cannot be used directly as columns, so we must explode them. And now we have the segments. Okay, so 15 levels, 49 floors. This is correct. And we have 10 different, let's say, vertical connections, depending on how many division we want in the number of segments for this divide curve. Okay, so we can also define any level slider in order to have more or less vertical connections, vertical elements. So once we have these, well, you can flatten them or not. It depends on how do you want to use them during your workflow. But in the end, the only thing that we miss is the definition of this column type. So I will copy this, plus I will copy the GG Revit column. So copy paste, move it here, place it here, plug the segment in the axis. You see that axis asks just for line representing column axis. Normally Grasshopper, when Grasshopper requires a specific data structure, like for example a list, it would say axis as list. But as it says only axis, it's irrelevant if you plug here a data tree or a list of elements. So flattening is optional. The only thing that I would recommend is that the moment that you want to use, for example, different parameters for different segments, then in that case, you might want to take into account what specific data structure you are plugging in axis and also in parameters or attributes or whatever. Okay, so let's turn on everything here, and we should get a whole bunch of columns. Well, in a while, they are pretty a huge amount of things right now. And so if we go closer or take a look at this from the top view, you see that we already have this column system or frame system climbing along the facade. There are several ways of obtaining this, and of course remember that now I'm using this this Revit profile, but you can use basically whatever thing you might want. So once again, we have changed to square hollow with thickness and fillet. So there are many ways of doing this in Grasshopper. I'm sure you're aware of this, but nevertheless, it's nice to play and to mix things up with between Revit and Grasshopper. And one thing is the orientation. So I told you I wanted also to consider the orientation of this, and the orientation is a vector. Now, remember that when you define a profile, it's good to have seen already that the profile, when you customize the profile, it appears in the origin of the coordinate system, and this profile has already principal axes like X and Y, which are important, especially when you want to define beams, beam orientation, and the cross-section orientation affects the properties of the beam behavior and resistance and structural characteristics. So it's important to understand that profiles are already they already have an orientation. Okay, and the orientation so it depends on the axis. So that's why orientation basically asks for a vector. Now we are working with a square hollow, so it's irrelevant if I change the orientation, okay? Because it's a square. Unless I want to create some weird inclination for this square and make it oriented with an angle with respect to the facade, which is something that I would not recommend for several reasons, also for assembling the structure or manufacturer proposes, but it's not the case eventually. So let's switch back to a standard, well, let's take another profile. So instead of using HD, which was good for columns, I'm now working with frames in general. So let's take IPE. Okay, so in order to have a clearer understanding of what is going to happen, I'm going to use this kind of profile. So it's a clearer what's the orientation of the object. Okay, so when we divide the curves, we not only have the points, we also have tangents. And tangents are orientation, which are basically tangent to the curve in the point where it's being divided. Okay, and this is happening at each level. Okay, so for each level, we now have the points, which are, by the way, generating the frame elements. So you see that, well, actually, it's being flipped. So these are the points. So 50, they generate the polylines with 49 segments, which are here. Okay. Now, remember this: we have 49 columns or axes. Therefore, we need a system of 49 orientations, which are defined by level. And for each level, the parameters, well, the tangent actually, is actually generating 50 elements, 50 branches, each one containing 11 tangents. So we must flip the matrix also for tangents in order to have a parallel flow and to avoid a misalignment of the amount of values. So these are 50 parameters per each vertical connection. So basically, it means that starting from the first connection, let me zoom here. Yeah, exactly. So remember that parameters are grouped, are 11 groups, because we have 11 vertical connections, basically. And we have 50 parameters because it's the first value refers to the parameters corresponding to the first curve. This is the second parameters, third parameter, fourth parameter. So we already have the parameters defined by the vertical connection. Okay, but remember that we have the fifth parameter here is not necessary, because the fifth column or the fifth frame element should start from here and go up, but we don't need it. Okay, so therefore we must avoid considering the last element. We can also call with an index from these lists. I'm going to call the 50th element. Now, remember that this is Grasshopper, so the first element is called 0, while the last one, instead of being 50, will be 49. Okay, so we can use as indices, we can place here an expression, x minus 1, and we can use exactly the amount of copies of our array in order to get rid of the last set of parameters. And so we should have 49 elements per each branch. So we have 49 per branch. You see that actually the data structure is absolutely consistent. So if I take a param viewer, you will see that there is a data tree with 11 branches. The branches have this index is the changing index, not the last one. And we have 49 elements. And if I change this, you will see exactly the same structure. Okay, so it's important also to maintain exactly the same structure when you do this kind of operation in order to have the exact correspondence between one input and the other input. Okay, and in order to avoid any possible mistake in this case, I would recommend that you simplify this data tree here and this data tree here. So whatever type of difference they have in the structure, it is now reduced because you only have one changing index, or the minimum amount of changing indexes necessary to define this kind of data structure. So if I do this, now we are orienting this section according to the tangent. Okay, so the tangent is becoming the rule for orienting what? Well, the vertical axis, the y-axis. Okay, so if you don't want this kind of orientation, it was impossible to see this with square hollow section, of course. But if you want this to be, let's say crossing through the facade, okay, then you must simply rotate these vectors. And in this case, you might want to make a simple rotation 90 degrees, but anyway, it's pretty straightforward. Okay, so orientation allows to change the orientation of the cross section. And in this case, it becomes consistent because at each level, the orientation is changing a little because we are changing a little the tangency in the point where the curve is being evaluated at the different heights. Okay, so that's why orientation can be useful. This thing here, Revit material, this is used if you want to override the material from the family type, from the column type, and you want to define it at the instance level. This is, well, let's say, this is something that is not so common, of course. The main reason, the principal reason why you use types and families in Revit is because you want to work with homogeneous sets of elements. Okay, so when you do this? Well, it could, but just to know how it works, if you define, for example, if you want to define a different material for each instance of this column, you can provide here the same set as we did with vectors, a set of 539 materials organized into 11 branches, each one containing 49 materials. Okay, and you can differentiate the material at the instance level. Now, this is something that normally you won't do, you will never do. But if you want, you can do this. And it's not like feeding the same GG-Revit column with all the axes and then defining the material for all the axes or all the columns together. The thing is that you might want eventually, I don't know, let's say that you want to have a different material from the bottom to the top of this tower. Okay, so you want some steel with some properties here at the bottom, and as you move towards the top of this tower, you can also decrease, for example, the, I don't know, performance of the steel. Okay, and so you can create a gradient of material properties from bottom to top. So in this case, for example, we are dealing here with our columns represented by 11 branches with 49 elements inside. If we reflip this matrix, we now have columns divided by level, by floor. So we have 11 columns divided into, 11 columns per level. So we have 49 floors in our tower. And so if we do this, we can also reflip the orientation, and we can also create the same data structure of materials. So we can create a data tree with 49 branches, each one containing just one material, where branch 0 will contain the strongest steel, and branch 48 will contain the weaker steel because it will be at the top. In order to double check this, we can explode the tree in order to see if we are considering the things properly. We should see only the ground levels, you see. So this is basically branch 0, this is basically branch 1. So branch 48 will be the last order of columns here at the top. And so if we create the same data tree structure, we can apply a different material to each level. Okay, but this is data manipulation in the end. So there is no rocket science here. It's just knowing how to deal with data trees. But yes, in that case, for example, that will be a smart move for defining a Revit material at the instance level. Okay, so we are not changing the shape eventually of the column. We are just changing the material at the instance level. So this is an override. Okay. Parameters and attributes, we are going to discuss them in the actual example that I have prepared in this multi-story building. But I hope this clarifies also in another application how you use columns and also with orientation. You must also, just in order to complete this and to have an alternative building to our multi-story building that I have here in purple, let's also define, for example, the levels, which is something that it's pretty straightforward. We already have here all the things that we need, because remember, we must create the level name. Then we must concatenate this using the proper separator, which is going to be space, it changes. And then we need a series of number. This series is going to start with 1. Remember to respect the Revit standards in order to avoid mistakes. And how many levels will we have? Is level are not floors, they are exactly level. So we need all the levels. So they are going to be 50. From level 1 to level 50. Okay, so these are going to be our levels, and the name is going to be this one. We just miss the elevation, and the elevation is defined by this. So basically, this is the floor height, and the elevation is going to be another series starting from 0 this time, because the first level will have the elevation at 0, like ground level. Step is going to be this one, and we need also the same amount as this. So the elevation will range between 0 and 245 meters. Wow, quite a tower. So here they are. We should see them at the center of our tower. Yes, here they are. We can also double check because they are, yes, there they are. Always double check when you do this, always double check that you don't have some weird behavior. So normally I do hide the grid, especially if the floors are in the center. Hide the grid and take a look if the frames are aligned with your with the corresponding level curve. Okay, because this is something that eventually, if it happens, it means that you by mistake you didn't specify the right amount of count here in the elevation, or there is some let's say discrepancy between the linear array in this case and the amount of elevation values that you are creating. Okay, just to double check that everything works perfectly. So these are the levels. Let's bring them here, or normally this is something that I didn't do in these files yet. Only here in the tower you see that I have this column of things, which, by the way, I don't know why they are yellow. Normally my personal color code, they are green. So you see that are all aligned, so it's very easy to understand where are the Revit geometries that must be baked. In this case, no, you see they are dispersed inside the definition, but normally it's a good option to keep these things, the final output at least, well, grouped together into one position. So I would say that this is basically defining Revit levels. Okay, so this is something that you might want to do in your definition in order to keep things clear. But this is the output. Now, the output doesn't necessarily have to stay here because it's actually only the final result. I prefer to keep this together with the other things that are important. Now, this is not important, for example, the column type. Okay, this is what is going to be sent as geometry preview. Also, for if you want to bake things in Grasshopper, you might want to bake this thing, the instance, not the type. The type has no geometrical preview. Okay, so if you do this, the only thing that I don't like is that if you bake this and they are 500 something columns, if you remember, and if you say you want to group them and hit OK, now you have these elements, but they are not grouped together. You see, I can still select them one by one. this is something I don't like. So the first thing that you might want to do is select everything and group everything in order to avoid unwanted consequences in your file. So yes, this is something that you might want to do, group the final output all together. So in this case, we have only columns and levels, but we can also enrich this with another simple thing. For example, so this is the general shape of the tower, which is basically up to here. Okay, so I will grab all of these things, group them, and this is going to be tower geometry, basically. So it has no intelligent feature; it's just pure geometry. So this is the first step, and then we have the column definition, which is a mix between Revit parameters and also Grasshopper technique for defining this the geometric aspect of our thing. So this is going to be another group. And so just in order to organize things a little, I'm going to move all of these things up here. Oh, I think by mistake I also included this, but this must not be part of this group. I noticed that something this remove from group doesn't work properly, so you might want to delete this. This is the geometry, and this is the definition for our columns or frame in general, because we are talking about the facade, so it can be in general named as a frame system. So let's add to this group. And so we have now another thing here, which is scribble. And this is, well, let's call this like facade frames in order to avoid any misunderstanding. So yeah, basically that's it, facade frame and the Revit levels, and here we have the tower geometry. So now, starting from this rotate here, which are all the, well, actually, it can be the rotate. It could also be the scale output. It doesn't matter because geometrically speaking, it's absolutely the same. So let's see what happens if we want to define Revit floors. Now, Revit floors are a little bit more complex because a floor is a composite element in Revit. Right? So you can create a floor as well as a wall as a composite element made up of several layers, each one with its own properties, right? So if you go, first of all, as always, instance. So Revit floor is going to be the instance. It's going to be the last of implementation. So you see column, level, and floors. And now, floor type. Let's go into element type, grab the floor type. You can already connect it. And now, things here are a little different. Okay, so name. Let's call this something like my floor. This is typical from programmers. Normally they add my nice floor. I don't know why, but anyway. So floor type, it wants to know the layers. Now, layers in a floor are, well, basically one layer in a floor defines not only the geometric aspect of this layer, like thickness, for example, it also defines material properties. Remember that in Revit, materials are not only used for rendering, of course, or for visualization, they are also used for deriving the physical properties and performance of a specific element. And so this is the case. So when you define a layer here in the floor type, you are defining not only the geometric aspect like thickness and so on, you are also defining the material and the performance of that layer. And so a layer is part of the stock. So if you go in Revit here, you will find material layer. Whenever you need to define a layer of something, be it a floor, but also a wall, so also wall types have layers, of course, you must use this material layer. And material layer has, once again, Revit material. And so you go here in the stock and grab a Revit material. You see how we are basically implementing backwards. I think this is easier when you start, but normally once you get the point, you will start probably by defining things progressively, like from left to right. Okay, but this is a good approach for those who are starting with Geometry Gym tools. So start from the instance and you go populating the inputs backward, like back propagation, something like that. So name of the material. So let's say that I want to define, for example, some finish layer. Okay, so this is going to be referring to my floor. This is going to be my floor finish. You can also give a description that is going to be present in Revit properties, instance properties, and type properties. You will see this once we import something in Revit. So I will say this, my floor finish description. Of course, you can add whatever type of details you might want to use here, especially if you want to use this information for creating schedules and quantities. Class. Now, class, it has the same things that we saw. Now we're not talking about structural element like columns and beams. So in this case, for example, this is finish. It could be, I don't know, ceramic. It depends on what finish you might want to consider. And it's important you define this from this point, and try to avoid, let's say, leave this information behind because, oh, I can edit this in Revit, because it's a little more complex to go looking for the elements in Revit and change these particular properties. You must go back and forth inside properties windows, and it's not that easy. Okay, so it's better to define this as soon as you define a material. So let's say we want to create a ceramic tiling floor finish. Okay, I remember that you can do this by right-clicking, but if you are going to create your own template for working for creating an interoperability workflow from Grasshopper to Revit, I do recommend that you implement a value list component, like name it material class, and here inside you will define exactly this type of thing. Ceramic equals 0, concrete equals 1, earth equals 2, and so on. So you will have this already plugged inside your component, and you will know that you must define the material class properly. Okay, so in my case, the only thing that I'm going to do, I'm going to use, what was it? 0 ceramic. Okay, so I would say ceramic equal 0. So you can choose the material by name and not by integer or by right-clicking here. Okay, so do this if you are creating your own template, because it's worth the effort. You do it once. It's a little bit boring because there are how many? 17 classes. So it's pretty boring to do this, but you do it just once. Then you can copy paste this whenever you need it in another file, or use the same template file for whatever interoperability process you might want to define. So material is going to be Revit material. Now, thickness is going to be the height or the thickness of this layer. Let's say we also want to define the global thickness of this floor. So we must consider that the global thickness at the type level is defined only by the name. So there is nothing here that allows you to define the general thickness of the floor. So the resulting thickness will be the sum of all the material layers that you are going to plug into layers here. So in this case, for example, ceramic tiles, I would say that it can be something like, I don't know, let's say not too gentle, like 2 centimeters thickness. Function. Another thing that I would populate with a value list, because it's something that is mandatory to define at the floor level. So you see that there is, so you see that there are basically 7 functions, from structure to structural deck. This is something that it's already present in Revit, and this is actually corresponding to what you have in Revit. So defining this property at this level allows reducing the effort once you have the elements inside Revit. Once again, create a value list. In this case, I'm going to grab exactly the right function, which is going to be 3 finish 1. Or 4 finish 2 maybe. But anyway, this is going to be the function. Maybe you might want to call this layer function. So in order to also recognize this if it gets disconnected from the component. And let's say I want finish 1 and finish 2. So 3 and 4. So I'm going to go here. Finish 1 is going to be 4. And also finish 2 is going to be 5. Yes, am I right? No, 3 and 4, sorry. So 3 here, 4 here. And so plug this here. This is better to have a visual approach to this, to defining this kind of things like class and function. Yes, Pepe, tell me.
About the thickness, do you need to put all the well in the layer thickness? Do you need to put all the materials in the floor, or just the finish, or how does it works if you have like the ceramic and the, I don't know, the concrete or whatever?
Yeah, yes, actually what we are going to do is exactly this. I mean, if you are into a preliminary project phase and you are not interested, for example, in defining layers inside your floor, you just define one single layer because it's mandatory. So you see that this component uh, is lacking the layers. Okay, so it asks for layers. If you want, you can avoid specifying the material, each one with its thickness, by defining a generic floor like it's already present in Revit. By the way, remember that if you name this generic, like generic 30 centimeters, for example, Revit will recognize this name, and inside Revit, it will assign the floor that it's being imported to that specific family. Okay, but anyway, you might want to do this already here in Grasshopper. So you just define one single material layer with the proper thickness, which is going to be, for example, 0.3 for a generic 30 centimeters floor, and you plug it here. But if you are defining a multi-layer, let's say, floor, then in this case, for example, if I don't plug thickness here, you see that it says that thickness is a mandatory parameter. So yes, you must define the thickness for each layer. Okay. I repeat, this is something.
But how do
Yeah.
you put
Tell me.
the different materials into that thickness? Because if you have like two
Oh, no,
materials,
no, 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 no,
you
no,
will
no,
have
no.
like
You don't put different
uh,
materials here. You create the different material layers, each one with its own material, with its own thickness. So the next step is going to be to copy paste this and create another material layer with its own material and its own thickness. Okay, in order to keep things separated.
and then both go to the layer
And both
in
go to
the,
the layers.
okay.
Yeah, exactly.
Okay.
And they go in order. Okay, because you must uh, plug these wires here in order to keep the exact order that you want in your floor. Okay.
Okay.
Okay, so this is enough for defining a material layer. You see that there are wraps. And this is another occasion where you see that there is a structural. And structural, once again, is by default set to true. Now, wraps, I will leave this to true, because this is something that, for example, allows Revit to understand if a particular layer wraps around a corner, for example. So I don't know if for some reason your floor is not connected to a wall, like this, and it ends like this. So there is, for example, some railing here, some balcony somehow. Then there will be the finish layer here. If you say that it wraps, it means that it can turn around the corner and also complete this finish here. Okay, so this is something that you might want to turn on, off, depending on what particular situation you are facing. But by default, it's set to true. So remember that this layer is capable of wrapping around a corner. Okay, so you might want to set these to true and leave it connected here. And for us, we don't want this to be structural. Okay, so this is a standard definition for the material layer. And we can plug this into layers. And you see that we already have this floor type. This is working. Now, this is not working because it misses the perimeter curve or the face if you already have solids or whatever. Okay, but I do recommend that you work with curves because it's easier and because this is already producing a solid. Okay, so we have our curves are the scale output or the rotate output. Actually, they are exactly the curve that have generated the cross section. So the columns. So eventually you might want to offset these curves outwards a little. So eventually let's create a small offset curve here, like this. I'm not going to take particular care about the distance, but eventually some 50 centimeters instead of 1 meter. Something like that. You can change it parametrically, of course. And these are going to be the curves that I want to use as floors. And so I plug these inside this component, and you see that we already have the floors visible. And these floors, if we go and see, they only have one finish layer. And so you see that the thickness of this is 2 centimeters. Okay, and now let's take a look at this. For example, I'm just to simply copy paste this without changing anything but the thickness. Okay, so 10 centimeters thickness, and plug this with shift into layers. So if we go here, let me see if I can visually have a preview of this. So this is 1 meter. Let me grab a distance. So let's measure by hand. It's not going to be precise, but nevertheless, this is 0.12. So exactly what we were expecting. Okay, so 10 centimeters and 2 centimeters. And now just take a look at this. What I want, also always consider that for some reason, especially when you create, for example, or you try to add several thicknesses or several things here, the output could also be in a data structure that is not capable of merging when you plug this into layers. So always double check that in this case, layers is asking for layers as list. Okay, so you must provide a list. If you do something before the material layer definition, you might have some non-mergeable flows here. So one thing that you can do, which is pretty rough, you can create a data container and you can plug all the wires here and flatten these and plug this into layers. Okay, so this gives you more control over the flattening or the data structure that is getting inside this layers thing. Or else you can flatten directly the input here. But whatever you feel more comfortable, well, just do this in an explicit way, because it's important to keep in mind that you must provide a list of layers. In which order are these layers here? Because you see that when you create the floor is just one single extrusion. Okay, so there is no possibility here to recognize the one layer from another. Okay, even if we create, for example, this is not going to be finished. Eventually, I want this to be a substrate, so I will further implement this with, what was it? It was one, right? One substrate. So I'm going to take substrate equal 1. So this is going to be substrate, correct? And it's going to have a well, eventually 5 centimeters. Sorry, 5 centimeters. You see that it is changing, and now you can understand what's the order. See, so you see that this is basically sorry, not the order. You can once again you can see what this does to the thickness, because the floor are extruded from the level down, of course. Okay, but you don't have any idea right now because you don't see the separation. Okay, so let me create a substrate which is correct and is not going. This is not going to be a finish. This is going to be substrate. Keep it consistent, or else you will get some undesired consequences. So this is going to be floor substrate. This is going to be floor substrate description, like this. And material class, of course, is not going to be ceramic. It can be already some concrete, or yes, it could be concrete, just to give it a name. It is concrete is 1. So double click here, concrete equals, oh, yeah, equals 1. And let's change it to concrete. Okay, so everything is consistent right now. And then let's create another one. So copy this, plug it here. Of course, the extrusion increases its height, but we have no idea yet of what's the order of these things. Let me grab a thickness of, in this case, I'm going to provide something like up to 20. So it's going to be exactly 20. This is going to be, in this case, it's going to be structure. So it's going to be 0. Structure equal 0. And it's already given. So function is structure. Thickness is 20. This is going to be my floor structure. Or you can name it whatever you want, right? So this is the material. Okay, it's not just a tag. And this is structure description. So remember that these are material definition. Okay, it's not tags. Okay, so we now have these floors which have become thicker, and now for the first time, let's go and have a look what happens when we want to export these things in Revit. So let's create our first well, export file, the IFC file. You see that these things here are the things that we might want to export. So once again, let's clearly identify them in order to better locate them inside our definition. You can use whatever method you want. This is my approach, okay? But you can come up with your own strategy, whatever you feel more comfortable for identifying this important element. How do we export things to Revit? We go into the Revit generic group of commands. And now, you see there are 4 bake things here, right? The traditional egg that represents the bake command. There are 4 different. Now, the one that we are going to use right now is bake to file, because we needed to create physical, well, in our drive, the IFC file, and then export it in another step, in a different step, into Revit. Okay. But if you are using Rhino inside Revit, which we are going to use the last day, then you can eventually bake to Revit and have your geometry directly imported and visible inside Revit without creating physically the IFC in your hard drive. Okay. So for now, we are going to use the bake to file. Bake to file, once again, this is something that normally I do group with a blob outline. Well, actually, this is something that eventually we must do only when you see that there are, for some reason, it always create a double group. I'm going to get rid of the first one. But anyway, this is the GGRA back to file, and it asks for a few things. I do recommend that you use or flag the IFC4 if it is not flagged. If you also want a CAD representation, a separate CAD representation, you can, oops, sorry. You can also select these SAT or DWG if you want to use this also for other purposes. But the important thing is to create in the IFC file. Okay. Here's my folder for this course. So let's double click here. The browser pop up. I'm going into our folder, and I'm going to name this like today, which is 17 me course, and this is going to be, well, I'm sure you're pretty familiar with this. I'm going to call this Foster. Okay, so this is going to be the IFC. It's already created. It's very light. It's very fast because there is some basic geometry. You see, it is just 400 kilobyte, so it's quite light as file size. But when you start creating more complex things, then in that case you might have heavier files as IFC export. And then let's go into Revit. This is, well, actually, I just opened this file, so you already saw it, but just remember that when you create this, do it with a template in meters. So we have a blank file, and if you have installed everything properly, you will have a Geometry Gym plugin here, and you will import IFC, select the IFC that you want to import. A window pops up with a bunch of options that we are not going to analyze here because it's not the case for this kind of very simple model. Just proceed. This will create on the fly. Eventually, you might see here some, you see, it's creating columns. Oh, it has also exported the columns, not only, of course, all the things that were turned on. So it might take some time right now because we have 500 columns. I didn't notice this, or I didn't pay attention. So you see that it's generating the columns with their respective families and all the instances. So it's going to run for quite a while right now. Okay, so they are sectioned and everything is working properly. If you want, you can also do some like aesthetic things like activating shadows and so on. I would recommend that you switch eventually to a fine visualization because when you work with, for example, with the composite elements like floors and so on, it's important to have not a volumetric representation of the objects, but a fine visualization with fine details. And now, of course, we wanted to double check, first of all, before going and analyzing this imported thing, which, by the way, we can also double check and go into a 3D viewport. And it's generating it for the first time. You see that we already have everything we need for our building. Okay, so this is it. Now, the first thing that we want to double check here are the floors. So let's go into the level one. Let's grab a section and let's section this floor at this level. So something like this. And let's go and see in this section, what do we have? Eventually, we might want to increase the width of this section box. And what I'm interested into is switching to the fine detail representation because what I want to see is this. And also get rid of the thickness of these lines. So you see, finish, the substrate and the structural part. Okay, so they are put in order from top to bottom.